as much of it as I wanted to for one reason or another, but I've been looking at some of the recorded materials. So without further ado, I'd like to introduce you now to the last talk in this session and the last session of the entire meeting. Toshiya Ueta talking about plasma diagnostics in the era of integral field spectroscopy. Over to you, Toshiya.
All right, thank you, Quentin, for that nice introduction. And let me show myself here. Hello, everyone. I'm Toshiya Ueta from University of Denver. And this will be something that I did during my sabbatical earlier this year at the Kyoto University. And then was supported by the Japan Society for the Promotion of Science. And then this work was done in collaboration with Masaaki, Otsuka, at Okaima Observatory. Okay, and then, by now, by these wonderful talks previous to me, we are all convinced that the IFU does wonderful things and then, marvelous things. And then, in order to get the best out of this nice data, we have to reduce the data in a very good way. And then this is a suggestion as to how we best to get out of the most and then from this wonderful data. Right? And then I will probably run out of time, so let me start off with this slide here, first one. And then so this talk is based off of this paper that I published last month. And then the upshot of this paper is open access, so you can go and then download. And then the upshot of this paper is that this paper outlines how best to analyze spatially resolved spectroscopy data, including IFU, but it doesn't have to be IFU. It can be done for any spectral imaging data set. And then if you follow this, what you need is just the data with your choice of the extinction law and in total to selective extinction RV value. Then you don't need anything else. You don't need any other assumptions or any other simplifications. You can just solve everything and then get the results. And then if you follow the traditional 1D data reduction scheme, then you may suffer from about uncertainties about 10% or even more. And then this is something that if you remember the first talk by Stavros, his plots have generally like 10%-ish error bars, and then that's what it is, right? So let me start off by going over how traditionally 1D plasma diagnostics was data reduction was done. So usually you start by assuming some sort of plasma that you're studying, and then typically people take some numbers, and then in this case, for example, 10,000 cc and so 1,000 cc and then 10,000 Kelvin, and then you use those numbers to compute the theoretical hydrogen line ratios. And you do that because you want to compare that with your observed line ratio, and then that will give you the amount of extinction, and then use that extinction to extinction correct your spectrum, and then use the extinction corrected spectrum to do the plasma diagnostics. And then usually you pick electron density diagnostic lines, and then to derive electron density, and then you pick electron temperature diagnostic lines, and then you derive the electron temperature. And then adapting these values that you derived, you go on to derive abundances and other quantities. That's how usually it goes in this traditional sense in 1D. And so I wanted to understand, so I'm new to this game, so I wanted to understand how we best, how we can do this in 2D, right? And then I looked around in the literature, and then people still start with this 1D scheme, and then you pick a number, and then electron density, electron temperature, and then you assume uniform density and temperature across the entire IFU field or entire field of view. And then this was something that struck me the most, because I'm the person who's interested in anything that is extended. And then, so I would not expect anything, uniform. And I want to study something that spatially varies, right? And then why do we want to use IFU? Because we want to study spatial variation of the target that we study. So why do we have to start by assuming this normal distribution? And that was something that struck me the most. And then, so if you do this, and then the rest is going to be compromised, because from the beginning, so this uniform distribution will give you the theoretical hydrogen line ratio that is uniform across. Then you compare that with your observed line ratio, and then to derive the extinction. So you don't expect your intrinsic line ratio is uniform. So your extinction value is already off. You know that. And if you use that to extinction correct your spectrum, then that is going to be off. And then if you use extinction corrected data that is slightly off, then everything else that follows is going to be off, right? So this is, so we are going to be, haunted by this initial assumption of this uniformity, and then this imposes this artificial uncertainty to our data. So this is something that we don't have to do. So I started looking at this closely. So this is how extinction correction is done. So you have this observed line ratio here, and then the intrinsic line ratio gets attenuated by respective extinction of the H. So in this case, H alpha and H beta, but it doesn't have to be this ratio, but I use this ratio. And then if you work this out, then expression looks like this. Right? And then you get this stage beta, the extinction value, and then this something else. And then let's see, I have to do this, right? So this is observed line ratio, and then this is theoretical line ratio. And then this bit, the blue bit here, this is the adapted extinction law. So this is something that is fixed by the choice of your extinction law. So in order to get the extinction value here, what we need is this theoretical line ratio. We really need to fix this very well. And then in order to do that, well, this is something that you can calculate. And then it says you need to integrate over the column with the emissivity, H alpha emissivity, and the H beta emissivity. So you have to do that. But the H alpha, H beta emissivities, they are actually dependent on the electron density and electron temperature. So what that means is that electron density and temperature are what you need to get the extinction value. But what are we doing? We are trying to get the extinction, what we are doing was trying to get the electron density and electron temperature from our data. So this is a classic catch-22 situation. We want to get the answer that we want are electron density and electron temperature, but we need these quantities to get the extinction, then do the extinction correction. So we need the answer to get the answer. So that's a classic catch-22 or chicken and egg. And then in order to resolve this, the one way to do this is to iteratively update your initial assumption of initial starting point, electron density, electron temperature, and then you iterate over to get these values converged. So this is one way to resolve this, to get out of this issue. And then the other thing is that, so in plasma diagnostics, we pick this so-called electron density diagnostic line ratios. And then so for electron density, but this line, this is actually, there's a temperature dependence to it. And then for the temperature diagnostic line ratios, you can get the temperature, but then there's also a density dependence. And it's very slight dependence, but still both of these things have dependence on both of these quantities. So again, here you have to do this iteration to come up with the converged solution. Right. So to case in point, so this is the intrinsic H alpha to H beta ratio plot according to various temperatures and then densities. So here in a log plot, and then the values do not change as much in the density way, but then still there is a variation. And then along the temperature, there is also a variation. So it's not a single value. You can't just pick a number and then use it for all the field of view. So what I suggest is the following. So I just named it as proper plasma analysis practice, PPAP. And this, as I said, this is just the iteration. So you start off with your extinction law and then the RV value, and then your initial starting point values of electron density and electron temperature, and then first get this intrinsic line ratio, and to get the extinction, and then do the extinction correction, and then do the plasma diagnostics iteratively, and then derive your first result of density and temperature, and then compare that with your initial result. And then if they match, you're done. But if not, then you need to go back and then update your value and then use these to get the intrinsic line ratio. And then you loop around until these values get converged. And then once converged, you're done. Right? So get this, get that, and get that, and then you're done. So then these quantities are not uniform across the nebula. And this is, and then also when you do this with IFU, you have to do this for each spark cell or each pixel. Right? So that's also a key. And then, so I tried this with the HST dataset, and I did this because I did this when I was stuck in my hotel room for 14 days for self-quarantine on my way to Kyoto in Tokyo. So I just wanted to do this real quick, so I knew I can get these data, and then so forth. So I did that, and then so I used I used H alpha H beta for the line ratio, and I used nitrogen 2 lines and then S2 lines for plasma diagnostics. And then if you do this convergence, and then you get the converged extinction map, and then this is converged the converged electron density map, then this is converged electron temperature map, right? Oops. So this extinction is not uniform at all across the nebula. So this is part of the ring nebula here. And then the structure is nice. And then you see these molecular knots kind of structures all around. And then this part is the radial distribution showing the density plot. So this shows the spread of the values at each radial bin. And then the value generally goes from about 0.2-ish to 0.4. And then increases, and then it's consistent with radiation field is strong inside and then weaker getting outside, right? And then the C value varies from about 0.2 to 0.4. So converting to the attenuation is about 30% to 70%. So if you just use normalized value across the nebula, then the result of extinction correction will be very off, right? And then also here, the ISM value for towards the direction of ring nebula is 0.1266. So now we have, indeed obtained the circumstellar component of the extinction here. So some people just pick ISM value for extinction and then use that to extinction correct their spectrum, but that's a huge no-no, and it's gonna underestimate your extinction. So then going to the electron density map, reasonably, for the first glance, it looks some kind of uniform, but then there's again the variation and a spread of about 1,000 cc or across. And then here, the temperature, we see this almost uniform distribution at the outer side of the nebula, about 10,000 K. So this is why people say the plasma is about 10,000 K, but there is a spread of values about 1,500 or 2,000 Kelvin, and so on, and that's the spread, right? And then here is the abundance maps. On the left, nitrogen plus abundance maps obtained from two different lines. The top one is from 6583, and then the middle one is 5755, and then the bottom one is the difference between the two. And then on the right, you have abundance maps of S plus, and then they are obtained from S2 of 6717 and then 6731, and then the difference. And then usually in 1D analysis, you don't necessarily get the same abundance from different lines of the different transition of the same species. And then people usually take the average and then call it the abundance of that species. But in this case, we got exactly the same distribution from different transitions of the same species. And then to me, this is a proof for this method to work. And then this is another test, if you will, of this analysis. And then these plots show how much abundance discrepancy you will get if you're studying, or if your temperature and then density are off. And then depending on how much off you get, how much discrepancy you get in the resulting abundance. This is that plot. And then this is the case of N plus abundance obtained from this N26583 line. And then the assuming that the true result, the density is 1000 cc, and then true temperature is 10,000 K. And then remember this, let's see, this is temperature. So let's go back to the temperature map. So we had the temperature spread is about 1500, 2000 K. So let's call 1000 up and down. So 1000 degrees off, right? 1000 degrees off, up and down, then you get 20% underestimate or 30% overestimate, right? And then similarly, on the right-hand side, this is the density side. So the density spread is about 1000, so 500 up and down. So let's go back, and then this is a true value here, and then if you off by 500 cc, then you get 40% uncertainty in your abundance analysis, right? So I hope that I convinced you that this is a good way to go to do the analysis. So this is just simple. I'm not, I'm not introducing anything special. I'm just saying that we can do this one by one, rigorously, and then numerically, and then you need to iterate over to get the convergence. And then, so that's all. And then I think I ran out of time, so I will just leave the summary slide and then be done with it. Thank you.
Thank you very much, Toshiya. Very great talk. I really enjoyed it. And it's good to see things being done properly and showing everybody how we should really be doing these calculations now. Thank you very much. So Stavros, you have a question. Stavros? Oh, you're clapping. Yes, you're clapping.
No, I was clapping, but you gave me the opportunity to ask. Very nice work. Very nice work. Really, it's a simple idea, but this is fundamental. So just a simple 500 or 100 particles per centimeter square in a density electron abundances, sorry, electron densities can result in a difference in abundances. Can you show the plot, the last?
Yeah, so I mean, this is, yeah, this plot, right?
Yes, it's huge.
Well, yeah, this is actually, dependent on your target, right? So, it depends on the conditions. So it depends on, it varies from a target to a target. But in this ring nebula case, if the discrepancy is 100 cc, then, well, you get like 10% uncertainty, right, in your abundance result.
Yeah, but I suppose this similar, and you cannot say for other objects, but for sure there will be some degree of discrepancy if we do not this iterational way to calculate the extinction coefficient for any object.
Yeah, so this 1D scheme was done back when, so then spatially integrated. So then this your spectra is made up of emission from different parts of the nebula, and then different very varying conditions. So your analysis is bound to have some uncertainty because you have a mixture of stuff. You're looking at mixture of stuff. But with the IFU, you're sort of lifting the degeneracy in the transverse direction, so you can do this better. So that's my point.
You're absolutely right. Thank you. Amazing.
Thank you. Raghavendra Sahay, you have a question?
Well, first, just a comment. Absolutely beautiful work, Toshi. I look forward to reading the paper, and I'm wondering, have you put this tool, made this tool publicly available? It'd be a great project to apply for other planetary.
Well, I've been asked the same thing for when I give this talk, but this is very fundamental, and I used just PyNeb that's available. So there's nothing special, so you can do this with any tools, or you can just do this by yourself or whatever. So, but I don't have a tool to make available right now. But you can just do this using the tools that's available already.
Okay, thanks.
Okay, any other questions from anyone? Can't see any others. Sure, there's no one else wants to say anything about this? I mean, are you planning to produce this PPAP system in a standalone environment that anybody can just, as I say, put in those few things that you say are necessary and run the thing, or are you just giving people a prescription and they can just do it themselves with various Python apps?
So you're asking me?
Yeah, I'm wondering. I mean, I think.
Well, so you know, when I went through this and I understood what was going on, the lesson that I learned was, because it was so kind of became a standard and it kind of became a myth in the field, and everybody just follows this almost blindly. And then so my lesson here is that you really need to do this yourself to understand what goes on. Otherwise, you will fall in the same trap again. And then so that's my my thinking about this. So that's why I don't have this specific tool for everyone to use at this point.
You'd be doing everybody a service if you did, but
I mean, I understand that, but then
you just want to teach people
take that into
what they need to
consideration.
learn. Okay. If there aren't any further questions for Toshiya Ueta, I think what we'd like everybody to clap our hands together for a great session and great speakers. I've enjoyed listening to all of them, and so this ends out the conference. So congratulations, everybody. Turn on your sound. Let's give everybody a clap. Well done, everyone. Fantastic, fantastic. So now I want to hand over to my dear friend Martin, who's going to finish off this meeting with a few announcements and observations. So over to you, Martin.